Hello friends, welcome to my channel. Now I would like to discuss the silicon control rectifier in Powertronic series of lectures. In the previous topic we discussed what is a power diode. So now I would like to discuss silicon control rectifier. So the difference between the power diode and silicon control rectifier is, so power diode is a uncontrolled switch and it is having only two layers. So three layers and two junctions. And in silicon control rectifier we are having three junctions called J1, J2, J3 and four layers. So P1, N-1, 3 as a P and fourth one as N plus layer. It is having three terminals known as anode, which is a positive terminal. So cathode, it's a negative terminal, and a gate signal here. So this is a controlling switch here. So in my first class I told you that powertronic devices are used for efficient conversion and control of electrical power. So here, so this part is of circuit is nothing but it's a control circuit. So control circuit is nothing but it's a low power circuit, and this is the main power circuit. So this is the main power circuit. So here in this region we can control a huge amount of power by using a small amount of gate signal here. So as we discussed, it is a semi-controlled switch. What is semi-controlled switch? So semi-controlled switch is a switch in which either on state or on off state, only one state can be controlled, remaining is not in our control. That's nothing but a semi-controlled switch. Yesterday we discussed the example for fully controlled switch is triac. So it's a semi-controlled switch. So we can turn on it, but we cannot turn it off by the normal techniques. So, okay. So here this is a semi-controlled switch. So there are three modes of operation to discuss about silicon control rectifier. Here, when the anode is positive with respect to cathode, so here we made anode positive with respect to cathode, then the junctions J1 and J3 are forward bias. So why the junction J3 forward bias? Forward bias means so positive connected to P type and a negative terminal connected to N type. So we can say that they are forward biased. Okay, but here when anode is connected to positive, so positive terminal is connected to P and the negative terminal is connected to N plus, so they are positive here. So junction J1 and J2 both are in forward bias. What about the junction J3? J3 is reverse bias. So during this condition J1 and J3 are forward biased and junction J3 is in reverse bias condition. So J2 is in reverse bias condition. So hence the SCR will be in off state. That means, so once the junction is in reverse bias state, no current will flow from anode to cathode. So this acts as a barrier in between the anode and cathode current, so that SCR is in off state. So during this period only a small leakage current will flow. So small leakage current flow, that's order of milliamps only. But when you are discussing about kiloamps, the milliamps is a very small quantity, we can neglect this one. That is what is called as leakage current. A small leakage current will flow. Next one, forward conduction mode. So in this forward conduction mode, the anode, the junction J2, which is early reverse biased, it is going to be avalanche breakdown and it enters into a forward biasing mode. That means conduction mode it enters. So during this condition, forward conduction mode, all the junctions J1, J2, J3 all are in forward biasing state. That means forward conduction state, so that the current will flow. So now here the anode and cathode get here. So it is one of the triggering methods of SCR, that is forward conduction mode. Anode is positive with respect to cathode and the gate current is 0 here. Okay, so when anode to cathode voltage is greater than the forward breakover voltage, so forward breakover voltage is denoted by VBO. For example, say it is say 50 volts. When you are applying VAK, say 52 volts, what will happen? That means it is more than that forward breakover voltage, so that SCR, the junction J2 is forward bias. That means it enters into reverse conduction state of the junction J2, so that directly we can say that the junction J2 vanishes, so that the ICR will conduct. But this type of conduction is not preferred. Why? Because it is damages the SCR completely. So junction J2 should be moved from reverse biasing state to reverse conduction state, not into destroy state. So we can avoid this one by applying gate signals here. Let's observe the characteristics of SCR here. So during this condition, here I told you that I am taking voltage on x-axis and current on y-axis here. So OE voltage across the thyristor here. So VBO is approximately infinity. So this is ideally speaking. So when the VBO breakover voltage in kilovolts here, a small leakage current is present here. It's nothing but leakage current, during which state it is in forward blocking state. When the junctions J1 and J3 are forward bias, J2 is in reverse bias condition, it enters in forward blocking state, and the current is edge 0. So when you increase the gate current here, by applying the gate signal, what will happen? So it enters into unstable region. So these dotted lines are unstable region. That means a switch should be in two states. A switch is a bistable circuit. So bistable means it should be either on in stable, or it should be in off, it should be stable. But here what is happening, the switch is in not in on state, sorry, off state here, and not in on state here. So in between these two states, it's called as unstable state. So here it is an unstable state here. Now we have seen the leakage current here, a small leakage current is flowing here, and here we define IA current. Now we'll see the point here. If the breakdown voltage, the breakdown occurs such a higher voltage without gate pulses, then the ACR may damage due to high power losses during turn on state. So why the high power losses, we'll see here. So next we'll see the significance of gate signal. So very important question if you are applying for any university exams or for IAS exams. What is the significance of gate signal here? In the gate signal, just observe here. So here the anode is positive, cathode is negative, means the ACR set to in which state? It is in forward blocking state. So in forward blocking state, J1 is in forward bias, J2 is in forward bias. Only junction here is, this part is nothing but the junction J2 is in reverse biasing state. Okay, now we apply gate signal here. What will happen if you are applying the gate signal? I am injecting the charge carriers in the junction so that we can decrease the depletion layer width here. So this reverse bias junction layer width is in, so we want to decrease this width. So by applying gate signal charges here, as a gate signal initiates, what will happen? It will distribute throughout this cross section area, so that it will make the conduction between anode to cathode like this. So these charges are the charge carriers which will make the conduction here. So initially the initial conduction area is very small like this here. If the gate current increases, what about the conduction area? So Ig is proportional to area. So area increases. As the area increases means, what about the dIg by dt? The change in current increases. Okay, so that dI by dt increases. So where the current is flowing? So this current is flowing and making the conduction like this. And what about the main current, the resistor current? It is entering like this. So both are going to be entered at this point here. So here the current will have, by applying KCL, it will have gate current plus anode current here. So as that change in current increases, initially rate increases here. So what about the gate current increases means, as more and more charge flows here, the quick the SCR will turn on. So turn on time decreases as the Ig increases. And what about the breakdown voltage? So breakdown voltage of the junction is very less as it increases here. So this is a conclusion here. As the gate current increases, breakover voltage or breakdown voltage decreases here. So this is the characteristics of our relationship that expresses between gate current and breakover voltage. So as the breakover voltage is maximum when the gate current is 0. As the gate current increases, the breakover voltage falls down like this here. Okay. So here we have some limits between the gate current Ig minimum as less than Ig and Ig max. So this is when we discuss the gate characteristics, right? So similarly, Vg minimum and is between Vg gate voltage is between Vg minimum and Vg maximum values for faithful or proper operation of SCR. So let's discuss what is a reverse blocking mode. So in reverse blocking mode, as we discussed, we are giving negative voltage to the P layer and positive voltage to cathode. So as we discussed that reverse blocking mode means, anode, that is anode means it's a positive terminal. Okay, so in forward bias condition. Now we'll give it as reverse negative. So anode is given to negative and cathode is given to positive here. So when you give anode to positive, so this junction is in reverse bias state and this junction is also reverse bias state. So junction J3 is reverse bias, and similarly junction J1 is also in reverse bias. Only the junction J2 is in forward bias. So as we discussed one point earlier in my previous lecture, that any junction having a lightly doped layer on either side of the junction requires larger breakdown voltage. Suppose if the junction is having higher doping concentrations at the both sides of the junction requires smaller breakdown voltage. So as per that rule, here the junction N plus is there and lower is N, so it requires lesser amount of voltage to break it down. And J2 is already in forward bias, and here also, so P plus N minus, so it's also require higher amount of voltage to break down here. So suppose the question is, what will happen if you give gate pulse when the reverse bias condition? Suppose if you give the gate pulse during reverse bias condition, what will happen? So see here, so as when you are applying the applied voltage here, gate signal is given, as you are applying negative voltage, that means reverse biased voltage here, this junction is having very thin layer. Why? Because if you observe the doping concentrations, they are both are high. So according to the doping concentrations, the junction having a highly doped layer on either side requires lesser breakdown voltage. So that junction J3 is damages here, and J2 is also forward bias here. So these two junctions are forward bias. The only remaining junction is in reverse bias is J1. So this junction J1 is in reverse bias state. So entire voltage has to be blocked by this junction J1. Suppose if you increase the VAK, this is a negative value. Okay, so if you increase the negative value of VAK again and again, what will happen here? So because of this increase in voltage, the junction is completely breakdown. So as it breakdowns means the SCR is completely damaged. So we should not give gate pulse when the SCR is in reverse blocking mode of operation. So here in this SCR, the only which mode is absent here is reverse conduction mode is absent here. So reverse conduction mode is absent in case of SCRs. Now we'll see the significance of latching current. So what is the meaning of latching current here? So latching current, it is an anode current only. So whatever the current flowing is nothing but it's a anode current. So latching current is related to turn on process. If you are writing any exam, theory exams, so it should be keyword for the exam. So turn on process should be there. So latching means it is always turn on process. So holding means turn off process. So here the gate pulse initiates the turn on process, but once the thyristor is in on state, the gate loses its control. That is why it is called as semi-controlled switch. Once because gate loses its control, so semi-controlled switch of the device. So therefore we can remove the gate pulses when the SCR become on, to avoid the continuous gate power losses. What will happen if you are giving continuous gate currents? The gate current will flow through this junction and will causes current crowding, and it will causes more heat dissipation across the junctions. So if the gate pulse is removed when the anode current is less than latching current, then the SCR fails to turn on. So therefore we must maintain gate pulses at least for a period of time to ensure that the SCR is in on state. The anode current reaches the latching current. So the key point is to turn on SCR, the anode current which is flowing should be greater than that of latching current. So this is specified by manufacturer. Say for example, say it's a 3 amps. So anode current should be 3.5 amps. You can see that SCR is in on state. Otherwise it's restricted as in off state only. Okay, so here we have taken the gate signal and the time period here. So we should maintain some minimum gate pulse here width to ensure that SCR is in on state. Now we'll see the significance of holding current. So holding current is something, it is related to which process? It is related to turn off process. So turn off, that means ACR is in enters into reverse blocking mode, or it may be in forward blocking mode. So always represents in blocking mode of operation. So gate has no control to turn off the ACR. So this is the reason why the ACR is said to be semi-controlled switch. The transistor stops conducting if the anode current reduces below the holding current. Okay, and you can see the example of half-wave rectifier. So here we can observe. So there are two currents, latching current and holding current. So there is no mathematical direct relationship between. We can derive it from the theoretical concepts, but we can say practically that latching current should be greater than that of holding current, and mathematically or approximately we can say that it is 2.52, 3 times that of holding current. So this is the empirical formula. So empirical formula which is derived from doing experiments, not from theoretical calculations. So this is the latching current is equal to 2.5 to 3 times of holding current. So this is a very important concept, and from this you can expect at least one question from this concept. So very important formula, latching current. So sometimes they will give holding current, and then sometimes they need to ask you to find what is a latching current. So this is things happens in general in case of PSUs. Okay, so here we'll discuss about the holding current, latching current. Now we'll discuss half-wave rectifier. So half-wave rectifier is taking as an example. So natural commutation. So commutation is a process by which we are making the ACR in off state. So how we are going to make the ACR in off state here? So we supply voltage, I is the anode current, thyristor on condition. So thyristor in this type of rectifier circuit, they use for natural commutation. So natural commutation means by the nature of supply itself, the ACR is going to be turned off. So here we are giving what is the nature of supply. Here you are giving DC supply. No, here you are giving AC supply here. So here we are giving the nature of supply as AC supply. So when the VAK is positive here, the ACR enters into forward blocking state. When we give gate current, it starts into forward conduction state like this, and the current starts flowing here. So as and when the supply nature here, VG becomes 0. So VS becomes 0 here. So when supply voltage becomes 0, automatically the switch enters into reverse blocking or forward blocking state. Okay, so this is the waveform here given. So this is nothing but natural commutation. So here the definition: in some of the cases, the nature of supply supports the commutation process. That means the nature of supply itself causes the ACR to be off condition, that is AC. So therefore it is known as natural commutation, or it is also known as line commutation. So line commutation. So commutation is the process by which ACR is getting turned off here. So if some cases the supply is DC, the natural commutation is not possible. So this happens in case of inverters and choppers. Why? Because there we have DC supply. Commutation circuits turn off the ACR, right? So in commutation circuits, reduces the anode current. How it's going to turn on? Reduces the anode current below the holding current and apply a reverse voltage across the ACR for making the turn off process faster, at least for a period until all the charges are completely removed here. That means whatever the charge carriers are stored at the junctions of the ACR and also in the layers, it is completely removed to regain its original position. So this process is known as commutation here. So let's see what is the circuit turn off time. It is a time for which the commutation circuit applies reverse voltage. So commutation circuit is a different circuit, so which we are going to so this is ACR. So we will use some commutation circuit here to control the ACR. So this is about commutation circuit to make that ACR is in off state. So it's a time for which the commutation circuit applies reverse voltage across the thyristor after anode current becomes 0. So very important here, at the instant after anode current becomes 0. So reverse recovery characteristics of ACR. So it is similar to that of what we see in case of a diode. The reverse recovery characteristic of SCR, it explains the switching behavior of the thyristor from on state to off state, switching behavior from on state to on state here. So here we have TRR, there is a reverse recovery time, and here we have TGR. We will see that what is a TGR and TRR. So TQ is a device turn off time, so TC is a circuit turn off time. So always remember here, the circuit turn off time is always greater than that of TQ here. What will happen if you not? We will see that. So during the excess charge carriers are present in the outer layers are removed. So during which period? So it is TRR, that is reverse recovery time. So SCR will have, so P N P N, so N minus, so P. So this is the structure here. So here we are giving the gate signal. So during this period TGR, during this process, the excess charge carriers are present in the outer layers. So these are the layers which are having excess charge carriers are removed here. Gate recovery time. So during this process, the charges are present near the gate junction. So near the gate junction here, they are removed. That means you have to completely remove TRR plus TGR in time, this time. So you have to remove all the excess charge carriers present in the device. Next one, device turn off time. So during this time, all the charges are completely removed from the devices. So TQ means is a combination of, so TQ is equal to TRR plus TGR. So during this period of time, all the charge carriers are removed. So device turn off time TQ decides the maximum switching speed of the thyristor. So if the TQ is very less, we can say that the switching speed is very high. So based on TQ, thyristors may be classified as, first one, inverter grade ACRs, second one, converter grade ACRs. Inverter grade ACRs having a switching off time is 3 microseconds to 50 microseconds, and the converter grade ACRs having 50 microseconds to 200 microseconds. That means they are slow and they are faster ACRs. So we can turn off and turn on very fastly. These are turn off and turn on, turn off very slowly here. So applications are used in inverters and choppers. So these are used in forced commutation techniques, and these are used in line commutation techniques. These are used in rectifiers and AC voltage controllers. And here you have a question which asks that, so what will happen if TC is greater than, TC is less than, that is circuit turn off time is less than device turn off time. That means we are giving very less amount of time to turn off by the circuit. So what is meant by commutation failure? So the answer for this question is, if the TC is less than TQ, the circuit turn off time is less than device turn off time, the commutation is not complete. Why? It is because some excess charge carriers are present still in the device, so they are not completely recovered. So there are some still charge carriers are present in the device. So because of charge carriers are present in the device, the next operation, if the anode is positive with respect to cathode, the ACR starts conducting immediately before the gate pulse is given. Even though you are not giving gate signal, the ACR enters into conduction mode. So conduction mode. So this is unwanted. This is not desired. So we are losing the control over the switch. So this is not undesired. So hence ACR behaves as a diode. So diode, and loses the forward blocking capability. So this is known as a commutation failure. Okay. So holding current, it's a minimum anode current below which ACR stops conducting. It regains the forward blocking capability of the device if TC is greater than TQ. So thank you friends, thanks for watching. If you like my videos, please subscribe and share with your friends and like. Thank you, have a nice day.